Hey there, in this little video we'll be going over the ballistic pendulum. This is a kind of neat little phenomenon where something like, let's say, a bullet, it gets fired, it has momentum, it's coming in with some mass and some velocity, so we have our initial momentum, and it hits a block, and it actually like embeds itself in the block. You can kind of see it in the more faint image here. So it embeds itself in the block, and it transfers its momentum and its energy over to the block. So now it's not just the bullet that's moving, it's the block and bullet that are moving. And then it swings up to some height and then stops. And then it turns back around and falls. And we don't really care about it after it hits the top here. And so looking at it, we have a bullet of mass 10 grams strikes the center of a ballistic pendulum of mass 2 kilograms. Already, that's kind of a drag. We have differing units here. We will have to convert those so that they're in the same units, so they're both at kilograms. The center of mass of the pendulum rises a vertical distance of 12 centimeters. Okay, great. A is asking us, calculate the initial speed of the bullet. What's the initial speed that it was moving before it hit, assuming it remains embedded in the pendulum? And then it asks us, suppose the bullet passes through. Okay, let's just do part A first. So we have A, and well, we're in the midst of a momentum unit. So maybe we just need to like apply conservation of momentum. And just for kind of sake of saving space on my page, I'm just going to do a little split down part of it here. And so before we kind of go ahead, let's do a little bit of a recap and put down a couple of things here. So in the beginning, this is our momentum. It's all in the bullet, m times v naught. That's what they gave us. And then afterwards, it hits right here into the block. And then it has some different momentum or some different velocity at least. Not different momentum, I apologize on that. And you would hopefully agree with me in identifying that it has to be going slower. And so we'd say that the momentum after here would be both masses added together, because it's all moving together, times v prime, whatever that is. And we know that even in inelastic collisions, which is what this is, momentum is conserved. So we have p equals p prime. Now there also is the second like process here, where once the block has been hit by the bullet, the block is moving. So actually right here, the moment the bullet is like embedded in it right there, let's not make that a circle. That was kind of weird. Like that. It now is moving. So right here, it has some kinetic energy, right? And the higher it goes, that kinetic energy diminishes. It gets smaller and smaller and smaller as it becomes potential energy due to gravity instead. And we know that potential energy due to gravity is mg delta y. This is what's on our equation sheet. And in your equation sheet, kinetic energy is 1/2 mv squared. So we kind of have two processes actually here. And since I haven't seen anything about air resistance where you have to take it into account, hopefully you would agree with me in identifying that these two energies are equal. The kinetic that's lost becomes potential, essentially due to gravity. So let's go back to the problem here, though, and we want to find the bullet, or the bullet's initial speed. So let's just go ahead and say, well, momentum is conserved. Let's just kind of start nice and easy. So conservation of momentum. And we're just going to start out by saying, well, P equals P prime. So the bullet's mass times its initial velocity equals the combined mass of the bullet and block times the velocity afterwards. And we're trying to find the initial speed of the bullet. So we want to find this V naught. So I would divide by the little m on both sides. And V naught is equal to m small plus m big times V prime over V naught. And it does not give us a velocity. We don't have a initial velocity here. And sorry, I am super tired actually right now. I totally just screwed that algebra up. This actually is little m on the bottom because we'd have to divide by little m on both sides to get the initial velocity alone. And so we know both the masses, and I'll just go ahead and convert them now. Going from grams to kilograms, we divide by 1,000. That's moved the decimal 3 spaces. So we still have our 10 with a 0, but now the decimal is 1, 2, 3. So we have 0.0100 kilograms. And likewise with our centimeters here, we divide by 100 and we get 0.1200 meters for it. So we know both the masses, but we have no idea what this final velocity is. So we're stuck. We're really kind of trapped here. We don't know what to do. And the only other thing that I could think of is applying conservation of energy and seeing if that helps us, just as we used last unit. So we have to compare the energies now. Now, I'm not saying that energy from the moment the bullet is fired to the moment the block and bullet hit the top is conserved. I'm saying that the moment the bullet is embedded in the block and the block starts moving, so the red up to the green, energy is conserved. There absolutely is energy that is lost as the bullet bores its way into the wood. And so the initial energy that's all kinetic of the bullet must be, or we would expect, is greater than the kinetic of the block and bullet together, or of the block and bullet at the tip top of this arc that it swings through. But for now, we're just going to compare the green and red. And here, energy has been conserved. So I'm going to say that our K, and I'll call it initial, is equal to the potential energy at the top. So we have 1/2, and wait, the mass, though, is both of them together. So now we have little m plus big M, and then V squared. But what V should we call this? Well, it's V after the collision. So this will be V prime squared is equal to, and then it's mg delta y, but now it's both masses times g, and then times this height, and they called it h in the problem, so we're still going to call it h. We're just going to stick to what they tell us to use. Now, luckily here, both sides, we have m little plus m big being multiplied, so those actually cancel out. Those kill each other off. That's kind of nice and convenient for us. And so really, we just have v prime squared over 2 is equal to gh. If I multiply by 2 and I take a square root, we get v prime is equal to 2gh with a square root. Do we know g? Yes. Do we know h? Yes. So v prime is equal to the square root of 2 times 9.8 meters per second squared times this 0.1200 meters. And I end up getting that our velocity is, rounding to 2 sig figs, 1.5 meters per second. So why do we do this? A is asking us, find the initial speed of the bullet. We just found the speed of the block and bullet together after the bullet got hit the block. But we can take this value, and now we can actually plug it in up top in our conservation of momentum. We now actually have everything on the right side of this equation so that we can solve for the initial speed of the bullet. And so we end up getting now to plug in our initial velocity is, I'm going to add my masses together now, 2 kilograms plus 0.0100, we end up getting 2.0100 kilograms times 1.5 meters per second over 0.0100 kilograms. And lo and behold, I get that our block's initial velocity was 301.5 5 meters per second. Now, if we were rounding to sig figs, this would be kind of an awkward one. We'd actually have to use scientific notation for it. Maybe we just leave it at 302 meters per second. So the bullet was flying. The bullet was going very quick. That's kind of close to the speed of sound. It's within like 50 meters per second. And now let's look at the next part. So we have a part B here. And before I move on, I do want to point out that this is a great problem because it's forcing us to look at a portion where energy is conserved, and there's another portion where energy isn't conserved, but momentum is conserved. And so we actually can apply both, looking at the overall phenomena here and recognizing that the kinetic energy, the velocity of the kinetic energy right after collision is the same as the velocity, after collision. And so this is kind of where these overlap. It's really in this kinetic energy part and this P prime part is how we were able to stitch those together and look at, oh, well, here's the energy portion. We can get something valuable from conservation of energy, and we can then plug it into conservation of momentum and ultimately get something that is asked of us, which is pretty awesome here. So looking at part B, it says, suppose the bullet passes through the pendulum. So it just punches through. It doesn't stay in it. Instead of remaining in it, yet the pendulum still rises a vertical distance of 12 centimeters. Indicate whether the initial speed of the bullet would have to be greater than, less than, or the same as what we calculated in part A. Well, if we think about this, if the bullet punches its way through and it's like over here, blasting along, it still has some momentum of its own afterwards. It's taken some momentum with it, and some kinetic energy, right? And so if that's the case, and it's like come all the way, just stabbed right through the whole block. If that's the case, the block doesn't have all of that momentum or energy anymore. It actually has a smaller percentage or kind of portion of it. And so in the first case, all the momentum transferred into the block with the bullet embedded. Now, the bullet is actually still taking some momentum away with it. Yet they're telling us the height is still the same. For that to be true, even though the bullet is passing through and stealing away some of the momentum, well, the bullet would have to be moving faster. It would have to be moving faster since it still has some of the momentum. So it would have to be a larger initial velocity of the bullet so that even though it's stealing away some momentum, the block still gets enough that it raises to the same exact height. And so I'll say it one more time. If the bullet passes through the block, then there's not as much of its momentum transferred to the block. So for the block to still swing up to the same height, the bullet must be traveling at a greater speed than before. Hopefully that made sense. Let me know what questions, concerns, fuzzy parts I have caused. And thanks for watching.